is the first video for AP Calculus BC on anti-differentiation or integration by parts. So integration by parts is essentially the product rule done in integral form. So you're going to need it when you've got two functions written as a product that you're trying to integrate. We've in the past been able to deal with this through U substitution, but as we discussed with U substitution, sometimes those two functions that are being multiplied are in no way related to each other, but we still need to be able to try to integrate, and so that is where integration by parts comes in. So let's look at product rule with derivatives and see how that can lead us backwards into integration by parts. So when you've got two functions, we'll call them u and v, and we're trying to take the derivative of the product of them, we would do the first function, which we'll call u, times the derivative of v. So that would be dv dx, and then plus the second function times the derivative of the first. So we'll call that du dx. So if I then take what I've written there in blue and I try to integrate that to come up with what the original function was, we would have if we integrate this and then we integrate all of this, well, the integral of the derivative of u times v is u times v, and then we would have the integral of u dv dx with respect to x plus the integral of v du dx with respect to x, because we would need to show what we were integrating with respect to. So that would become u times v equals the integral. These dx's are going to cancel to where we just have u times dv plus the integral of, again, these dx's are going to cancel, so it becomes v times du. So at this point, we essentially have an equation of the relationship. But if you're doing an integration by parts problem, the problem is not going to say uv equals, find what it equals. The problem is going to say find this integral. So for example, if they wanted us to solve for this one, we could get the integral of u dv by itself by taking the other integral and subtracting it to the other side. So this is our integration by parts formula. If we have two things that we're integrating that are distinctly separate but being multiplied, one of them we see as an actual function u, and the other one we think of as the derivative of some unknown function v that we're trying to integrate. So the next slide just shows you that formula again that we just came up with, u times v minus the integral of v du. It's essentially a formula. You're just going to need to know what that formula is, how to do it. It's just like memorizing some of our derivatives we've had to memorize. You need to memorize this integration by parts formula. And the best way to memorize it is to practice it. So here, for example, I have the integral of x cosine x dx. If this was on any random paper and I was told to integrate it, the first thing I would do is look at it and see if u substitution was an option. X and cosine x are in no way related to each other in terms of one being a derivative or some form of the derivative of the other. They are very distinct, separate functions. So that tells me that I have to do integration by parts. So one of those is going to have to represent my u function, and the other one is going to have to represent my dv function. It doesn't really matter which you choose as which. Typically, when I'm choosing, the dv is where I start because I want to pick something that's relatively easy for me to integrate. In this case, though, both the x is easy to integrate and so is cosine of x. So it really doesn't matter what you choose, which you make your u and which you make your dv. It should all work out in the end. So I'm just going to go in the order I see them. So I'll make the u be x, and the dv will be cosine x dx. Now to finish out my formula, I'm going to need to know what du is, and I'm going to need to know what v is. So du is just going to be the derivative of u, which is x. So the derivative of x is 1 dx because it's with respect to x. The dv, to go backwards to v, I need to integrate it. So cosine of x is the derivative of sine x. So v is equal to sine x. So now I just remember that my formula for u dv is u times v minus the integral of v du. So that means that the integral of x cosine x dx is the u that I came up with times the v that I came up with minus the integral of the v that I came up with times the du that I came up with. Now notice I'm not done because I still have an integral sign on the right-hand side of my equal sign. So until I've integrated everything, I'm not done with the problem. So I still have my x sine x here minus the integral of sine x. Well, sine of x is the derivative of negative cosine x. And now that I've integrated everything, I'm going to put a plus c at the end. So that becomes x sine of x plus cosine of x plus c. And if you swapped your x and your dv differently from mine, I still encourage you to work it the other way and see if you end up with the same answer I do. You should, but feel free to give it a try. So let's think through some things. What if I had chosen my u to be 1 and my dv to be x cosine of x dx? Well, if I had done that, then du would be 0 dx, and v, I would have to integrate this to figure out what v is. I would then be stuck because I'm integrating the same thing that I've been trying to integrate since the beginning of the problem, and I have no way to do that. So that's why that combination wouldn't work. Okay, so what if we had used u was equal to cosine of x and dv was equal to dx? So that would make du, I would have to do product rule, so that would be x times negative sine x plus cosine of x times 1. And then dv, when I integrate that backwards, 1 dx would integrate back to an x. So my formula would be u times v minus the integral of v du. Notice when I do it that way, the integral that I now have on my paper to integrate is more complicated than the one I started with at the beginning of the problem. You don't want to make something more complicated than it already is originally. So that would not be a good combination. So what if we had chosen the opposite order like I was talking about? Well, du would be negative sine x dx, and v would be 1/2 x squared. So u times v would be 1/2 x squared cosine x minus the integral of v, and since that's a minus sine x dx, I'm going to make that a plus sine x dx. Well, even though I said you could have chosen in the opposite order, look at it now. Just like the one I was looking at a minute ago at the top of the screen there, that integral I now have is more complicated than the one I started with at the beginning of the problem. My whole goal is to make my integral easier to do. So using that combination is going to make it more difficult on you. So if you ever choose in one order and it looks like it's just going to continue to get hard, try swapping what you chose to be your u and your dv to the other combination. So that would be why u equals x and dv equals cosine of x are good choices, because they make the resulting integral easier and able for you to integrate pretty simply. Okay, so that kind of gets summed up on this slide. The whole goal of integration by parts is to go from a complicated integral that we don't see how to evaluate to a simpler one that we actually can evaluate. But sometimes integration by parts doesn't work, and sometimes we have to do it multiple times in order to evaluate an integral. For example, here, I have the integral of x squared e to the x dx that I'm trying to evaluate. So I am going to try just the order that it shows up. I'm going to make my u be x squared and my dv be e to the x, because e to the x is easy to integrate. It's just going to integrate back to itself. And x squared is easy to differentiate. It becomes simpler when I do it. So I would have the integral of x squared e to the x dx is equal to u times v minus the integral of v du. So x squared e to the x, that's nice and easy. Now I'm looking at the integral that I have, e to the x times 2x. I still have two functions being multiplied that are in no way related to each other inside of that integral there. So let's try using integration by parts on them. And typically you try to stick with the same u dv combination that you were using the first go around. So we had the e portion as our dv, and we had the polynomial portion as our u. So in this case, u would be 2x, so du would be 2 dx. And if dv is e to the x again, then that would make v e to the x. So that makes my integral x squared e to the x minus this u times this v minus the integral of this v times this du. So we have x squared e to the x minus 2x e to the x. And now when we come to this red integral here, we would have minus a negative, so that would become plus. And then to integrate e to the x times 2 dx, this is just 2e to the x dx. 2 is a coefficient, so we bring them along. And then e to the x just integrates back to itself. And now that we've integrated everything, you can put a plus c on it. So you actually end up with 3 terms for that guy. All right, so that completes the first video on integration by parts. We will pick up with tabular integration, which is a simplified form of integration by parts that you can't always use, but when you can use it, it's very helpful.